We started.
Okay, thank you, and thanks for the organizers, and also thanks to Lou Kaufman for all the great ideas over the years. Um, One of those great, we've all heard of the Temperley-Lieb algebra, and I think most of us are familiar with it from its diagrammatic point of view, but my understanding is that it was actually Kaufman's idea that Temperley-Lieb had to do with curves and isotopies in the plane. And I think the theme of this talk is whether we can do something similar in higher dimensions. And so pointer, if you're bored with the preliminaries, you can try to think of why this relation, what's special about that. Okay, so let me just remind you of some things we already know. Given a disk with a boundary condition, which is some number of points in the boundary, we can form a vector space. It's the span of ways of connecting up the points with arcs. And if for some reason we found a closed component somewhere in there, we would replace it with a scalar, d or delta. I should also say I'm doing the purely two-dimensional version of this, so I'm not going to consider crossings here. And so the dimension of this vector space is a Catalan number, which will be z. If C is odd, it's zero dimensional. Otherwise, it's a Catalan number, which have a lot of interesting combinatorial properties. These diagrams could be glued together, and so that gives some kind of algebraic operations on these vector spaces, and the boundary conditions can also be glued together. And if you were to sort of formalize these properties, that's where this two category comes from. So we have a two category, a tensor category. And then just there's general theory that if you have an n category, some kind of algebraic gadget that behaves like gluing n-dimensional balls together, then that gives rise to what's called an n plus epsilon dimensional TQ of T. It's this probably the fully extended TQ that you're familiar with, except the top dimensional part, the path integral, is not necessarily there. And some pieces of that structure are we can form a skein module for a surface. We fix a boundary condition and then consider curves inside modulo the relations that we looked at above. If we have a one manifold, we can form a linear, there aren't very many one manifolds, so say the interval or the circle. And then we can form a cylinder category whose objects are these codimension one unoriented submanifolds of our one manifold X. And the morphism spaces are, we put the boundary conditions on top and bottom and then do the same construction as in the previous slide, and composition is stacking these cylinders. And then there's also a path integral that's not defined. If so far I'm using the sort of generic parameter Temperley-Lieb. So this path integral is only defined for certain three manifolds. In particular, it's if the three manifold can be built out of zero handles and one handles. And if we take some quotients, we can maybe define it beyond that. So that's all old stuff. Some more old stuff is that we can build a family of orthogonal polynomials starting from this. And this orthogonal part is related to the fact that we can understand one handles three-dimensionally, even for a generic parameter. So first thing we want to do is look at what are the idempotents of this category for the interval, and they are familiar. Kaufman has a great book with Lenz about working these out, starting just with first principles, often called Jones-Wentzel idempotents. And so now if we take the skein space of a cylinder with empty boundary conditions, we can construct two different bases of it. One is the sort of obvious topological basis. We can take a ring and I'm calling it R squared because this is composition in the category, stacking. So we've got all the powers of R. And it's pretty easy to convince yourself that you have an arbitrary one manifold in the cylinder, then it's equal to something like this up to a factor. Um, and so we get a polynomial algebra on one variable in this case. But there's also a basis we can get from taking the idempotents from the previous slide and closing them up. And so and these have the property that they're orthogonal with respect to a trace or inner product, that in some sense, I'm not going to go into it too much, but this is somehow the path integral of a disk across a circle. S1 cross B2 gives us this inner product, and so these are orthogonal, and if we express one of these in terms of one of these, we get a family of polynomials that's orthogonal, and these are, of course, well-known Chebyshev polynomials. And then we also get a measure on the real line, because this is a one-variable polynomial thing, and as is well-known, we get a measure which looks like the semicircle. Another thing we can do with Temperley-Lieb is look for quotients, and maybe quotients that make the whole thing more finite. So a tensor ideal, or the kinds of relations we want to look at, are tensor ideals in the sense that if G is some linear combination of diagrams that we declare to be zero, then anything that we can get from G by gluing something else on, like H, had better also be zero. If we have such an ideal, we can look for a generator that has the smallest possible boundary condition. And if that's true, then this generator needs to be zero for any cap that we can put on the outside. And that gives some equations that we can try to solve. And the first two solutions, well, the first solution looks like this. And that leads to a TQ of T that looks like Z2 homology. So this is not very exciting. It's just a repackaging of classical invariance. But the next solution with 6 points on the boundary yields the so-called Ising TQFT, or maybe the double of it. And it's much studied in quantum computation, and it's an interesting thing. So one of the goals of the talk is to try to do this in higher dimensions. And in general, we have a family of solutions, one for each root of unity. And for these finite quotients, and this is something that's not going to be true in higher dimensions, as far as I know, but we actually get a full TQFT defined for all three manifolds once we mod out by one of these tensor ideals. Okay, so now finally, the goal of the talk is to try to generalize all that, including A and B, to higher dimensions. And then the question is it an interesting generalization? And I think spoiler alert, my answer is maybe. I'm not. It shows signs of being interesting, but it seems kind of halfway in between, clearly interesting and clearly not interesting. But I'm going to try to make the case for interesting. Okay, so what higher dimensional Temperley-Lieb is built out of codimension 1 submanifolds of a two-dimensional ball. And so this higher Temperley-Lieb, we're going to take codimension k submanifolds of an n-dimensional ball. And what kind of local relations do we want to put on there? So let me rephrase Temperley-Lieb in a way that obviously generalizes to higher dimensions. It's built out of codimension 1 submanifolds y of the ball. And if we see a closed component, then we replace it, we can erase it, and we get a scalar delta. And then y and y prime are considered the same. I don't want to say isotopy. I want to say they're the same if they induce the same partition, hence partition relations in the title, of the path components of the boundary of y. And if you say, and so that it's easy to see that just gives the same old Temperley-Lieb. We've just said it a little bit differently, but the advantage of saying it that way is it obviously generalizes, and it has a two-parameter family of generalizations. We can consider codimension k submanifolds, and we consider balls in any dimensions. We can still get rid of closed components. Oh, this should be I'm going to call this beta for the rest of the talk. Let's see if I can fix that. We consider this is the main relation, two manifolds in the ball are considered the same if they induce the same partition on their boundary. So this is a very coarse, it's a big hammer. It makes a lot of knotted surfaces just all become the same. But if you want a finite dimensional space, you need to do that, because if you're only modding out, say, by isotopy, clearly there's infinitely many isotopy classes of codimension K submanifolds in the M-ball for most values of K and M. So to look at the relation again, we've got some codimension K submanifold, and then we say that two path components of the boundary are in the same block of a partition if and only if they are connected in Y. So this surface where it looks like this would give rise to the partition where A and B is one block and C, D, E is the other block. And so now we can define a vector space, which is surfaces modulo these relations. And also, if we get rid of a closed component, we get a factor of beta. So again, the summary of these relations, once more, if I erase this guy, then I multiply by beta, and this is my very poor drawing of two surfaces which are totally different except in the way that they connect over the boundary components, and they're considered the same. Okay, so all of this behaves well with gluing, so that means there's an associated n plus epsilon dimensional TQ of T, just for free. And we can define a vector space for an n-dimensional manifold basically by taking a co-limit. We consider codimension K submanifolds of M with a fixed boundary condition, and we consider them the same if you can get from one to the other via a series of partition preserving modifications within an n-ball. And similarly, we can define a category for an n-1 manifold whose objects are the codimension K submanifolds of Y, and morphisms are this vector space applied to this particular n-manifold, where the boundary conditions are A and B, the objects. So that's all just sort of standard machinery. And we even get a little bit of the path integral, because I said I chose a very coarse or powerful equivalency relation, and so the vector spaces I get for the ball are finite dimensional. That wouldn't be true for all n manifolds, but it is true for the ball with any boundary conditions, and that means that I can define the path integral for, I know what the path integral does when I attach a one handle. And an interesting question is whether for quotients we can extend it beyond just 0 and 1 handles. So we've got this two-parameter family of theories. When n is equal to 2 and k equals 1, it gives temporally Lieb, which we already know is interesting. What about all the rest of it? And so most of the rest of this talk is going to be about the n equals 3, k equals 1k. So that would be surfaces inside 3 manifolds. And if there's time, I'll also talk about n equals 4, k equals 2. That would be surfaces inside 4 manifolds. So usually around here, I encourage questions. I think the moderators disagreed, but if anyone wants to break the rules and ask questions, I certainly will not mind. Okay, so what are these vector spaces? In the temporally Lieb case, classical temporally Lieb, their dimensions will be given by Catalan numbers. What is it when n equals 3 and k is equal to 1? So let's look at a boundary condition. A boundary condition in that case is a collection of circles in the boundary of the 3-ball. And up to isotopy, if we take the dual graph, a vertex for each region and an edge for each circle, these are the same as unrooted trees. So for example, you should think of this picture as being in the 2-sphere, and then the dual graph looks like this tree. And if I have this picture, which up to isotopy in the 2-sphere is the same as, is the same as this picture, then it's this tree here. And so we define the D, the dimension function of a tree. And so for most of the talk, I'm going to say tree, but I'm not making a distinction between a tree like this and a collection of circles in the two-sphere like this. So I'm just going to constantly go back and forth. And D of T is defined to be the dimension of this space. So some higher dimensional version of a Catalan number. And it's the number, we know the maximal dimension would be the set of all possible partitions of the edges of the tree. The edges of the tree correspond to the circles. But not all of those partitions could be realizable by submanifolds. And so for example, here when I've got three unnested circles, it's easy to see that any partition can be realized by surfaces. But in this case, if I wanted to say that the innermost circle and the outer circle are joined together, and then I also want this middle circle to be bound to surface disjointly from that, that's not possible. So the Catalan number associated to this tree is 4 rather than 5. And so just some photocopies of old notes so here's what we just discussed. Actually, no, here's what we just discussed. And you can just work these out by hand and you see that, okay, at least they're not all equal and they're not familiar numbers. So maybe this is some kind of interesting theory. And one can go on and compute more and more. And then you get tired of doing it by hand. And so you write a computer program that computes it for you. This is some kind of encoding of a tree. And here is the trees drawn. And again, we have a collection of interesting numbers. And so the combinatorial description of this vector space as a partition is admissible, i.e. realizable by surfaces, if and only if for all edges in the same block. So remember, we're looking at partitions of the edges of the tree. So for example, here's an edge that's part of block A. Here's another edge that's part of block A. And then there's a unique path joining them. And that path, if we look at the other parts that appear on it, other than A, there should be an even number of each one. And if that's true, then it's easy to see you can construct a surface that realizes this partition. Okay, so now that we understand these sort of the spaces for a 3-ball, the next thing we want to do is look at idempotence of, say, the category associated to a disk with a boundary condition. So recall that, just by general TKFT stuff, we're going to have a category for any surface. The simplest surface I can think of is a disk, but the disk has boundary conditions, some even number of points in the boundary. And so let's take the simplest one, c equals 0. So a disk with empty boundary. And so now the objects are going to be collections of circles in the disk. And these are the same thing as rooted trees because the region somehow, the outer region is distinguished. That's the purple one. So here I've drawn up various collections of circles. Here's the corresponding rooted trees. And the dimension of the morphism space from a tree T1 to a tree T2 is this dimension function, this function I was drawing up here for the, I'm not a graph theorist, so, oops, if I take two rooted trees and I join them at the root, that's what I mean by this. There's probably a name for it, but I don't know what it is. So for example, if we want morphisms from the collection of circles corresponding to this tree to that tree, it's the dimension function of this, which happens to be 10. Okay, so we want to understand what all the minimal idempotents are of this category. What I did now is just describe the objects of the category and give kind of a more combinatorial definition to go along with this topological definition. But if we have a complete set of idempotents, then a given rooted tree or collection of circles is going to be isomorphic to a direct sum of those idempotents, simple objects with a coefficient given by the vector space, which is the HOMs from the idempotent to the tree. So that's just general semi-simple category stuff. And then it follows that this morphism space can be written as this sort of dot product of those two columns of numbers. I guess I've just written that out here as well. And so for example, okay, so again, this photocopy from some old notes. On the, what is this table? I think if I did it for the usual temporally Lieb category, it'd be familiar, but on the bottom I have objects. So various collections of circles in the disk, which you can think of as trees if you like. And on the vertical axis, I have idempotents, and this is just some graphical notation I have for idempotents. And these are quantum dimensions, but I'm not going to really talk about them in the talk. And so, for example, if we look at the maps from two unnested circles to itself, we know that the total dimension should be 15 because that's how many partitions there are. And for this configuration, there's no restrictions. And indeed, 1 squared plus 1 squared plus the dot product of this column with itself is indeed 15. And if we take dot product of two things here, then we'll get that capital D number for the corresponding tree. So this is computable. I guess that's the point. And similarly, if we have 2 points, then we get circles with an arc going across, and we can think of two different trees, T1 and T2, and the two sides of the arc. We can do similar stuff, and for D equals 4. Okay, so what does the general case look like? So what's the theorem for the idempotent of the category, this category for any boundary condition? Let me first do it with the empty boundary condition. So T be a rooted tree. It's got a group of symmetries, isomorphisms of the tree, which fix the root. And given an element of the symmetry of T, we also want to think of the surface that sort of draws that symmetry as a bunch of cylinders in D2 cross I. D2 cross I, and we have cylinders going like this, maybe another cylinder going like that. And now let's choose an irreducible representation of this finite group and take the corresponding idempotent or minimal idempotent in the group algebra. Then, just by usual ideas that will be familiar from lower dimensional examples, there exists a minimal idempotent of this category whose leading term, highest order terms, look like f sub p. And then we have some lower order terms, and by lower order, I mean that we can cut them in a way that has fewer circles. So if we were doing the usual temporally Lieb, this would just be some kind of trivial idempotent. This would be the identity graph, and then we would have lower order terms that have a narrower waist, and the logic is just the same in this case. And so the theorem is the classification of minimal idempotents for the D2 with empty boundary conditions, that list of idempotents that I constructed above is everything. And there's similar results for the other boundary conditions. You just have to give the tree irrep data and each component, each complement of these arcs, and also consider all configurations of arcs. Okay, so now that we understand the minimal idempotents, we're halfway to that construction of Chebyshev polynomials. The other half of that is to understand the vector space, say, of S1 cross B2 in a more topological way. So, if we've got I've got a cylinder, B2 cross I, and I have some collection of circles, and then I have some automorphism of them, like I've drawn here, then I can glue it up to get a collection of surfaces in S1 cross B2. Here's a more complicated example. And each of these can be these things are indexed by a tree, as we discussed before, and an automorphism of the tree. So for example, here I take the tree and I swap these two leaves and I leave this one alone, and that would give this diagram. This here, we've got a more complicated tree, and so I would swap these two lower edges. That's the sort of big orange crossover. And then I might do some kind of permutation of these 6 twigs, which correspond to these 6 circles here. And so in general, given any rooted tree and a symmetry of it, I can form the closure as in the figure above. And that gives an element of this skein module, this 3-dimensional skein module. And 2 closures are the same if and only if alpha and alpha prime are conjugate in SimT. Again, that's pretty easy. We can multiply these things together on trees. It corresponds to that, joining the root vertex together. Topologically, we just juxtapose them. And in the primitive elements under this multiplication, it's primitive if and only if alpha has a single orbit near the root of the tree. So what I mean by, like, for example, because this guy will be primitive, and we don't have to worry about the details of what it's doing to the purple components, because we know that near the root of the tree, the 2 orange components of our circles, it has a single orbit. And so there's no way to factorize it by multiplication. This one, on the other hand, is factorizable because there's 2 orbits. There's the orbit of these 2 edges and the single one here. And so this picture is somehow equal to this picture times a picture that just swapped those. And so the theorem is these closures are a basis, but the algebraic structure is a commutative polynomial algebra whose generators are the primitive automorphisms as just defined. Okay, so now we have, if our goal is to construct an interesting family of orthogonal polynomials, we have the algebraic basis, we have the polynomial basis, but we also need to measure. And I'm because of general TQFT nonsense, we know that we can compute the path integral of the 4-manifold B3 cross S1. That gives an inner product on the space, and the idempotents are orthogonal. And I'm guessing a lot of the audience is familiar with that idea in lower dimensional examples, and my assertion is, the proof works just fine in higher dimensions as well. Okay, and so then putting it all together, that we have a family of orthogonal polynomials where the variables of the polynomials are indexed by pairs rooted tree, comma, automorphism, and this is a conjugacy class of primitive automorphisms or symmetries of the tree. So that's how the variables are indexed. And then the polynomials are indexed by pairs, again, a rooted tree, but this time I want an irrep of the full symmetry group. So I think when some ancestor of this talk was to an audience full of combinatorialists, and so hence the emphasis on orthogonal polynomials. Okay, so now let's say something that might be more interesting to topologists. What about quotients? We know for regular temporally Lieb that we can classify the tensor ideals, and we get pretty interesting 3-manifold invariants by modding out by that tensor ideal. And so here what I want to do is I will classify the tensor ideals, but I'm not sure what to say about the corresponding manifold invariants. So we've got some generators. So this is some linear combination of surfaces. and I want it to be a minimal generator of the ideal. And so for temporally Lieb, I won't go back to the slide, but we had a disk with dots on the boundary, and then whenever we capped here or capped here, we get 0. Here we can cap off a single gap boundary component if it's an innermost circle, but we can also do a saddle that reduces the number of circles, and both of those simplify the boundary. And so if this is a minimal generator, we know that this linear combination better be equal to 0 for all caps and for all saddles. And these are joining saddles, meaning they reduce the number of circles. And if the number of circles on the boundary is small, you can just solve this by hand. So the first thing we discover is yet another way of arriving at Z2 homology. We can take a generator to be this linear combination, cylinder minus 2 disks. And that will be a generator if we set the parameter beta equal to 1. And that clearly, if we take surfaces modulo the relation that this is equal to this, we just get homology, Z2 homology classes of circles. Not interesting. Well, what's the next example? And for this set of boundary conditions, 3 unlinked circles, we can take this linear combination, and you can check that also has the property. So this is a sensible relation to impose on surfaces. And I want to emphasize I'm imposing this relation and the partition relations and the closed components or scalar relations. And so the theorem is that we get a minimal ideal generator G. It exists if and only if beta is a positive or non-negative integer. And the boundary condition has to be a tree of constant non-twig valence. So here's an example where everything is 4-valent, except for the twigs of the tree, which are 1-valent, of course. So the simplest trees look like this. And so the beta equals 2 example is what I've drawn up here, but one can do that, and in fact, one can write it explicitly for these simple trees, which correspond to maximal ideals. The coefficients, if I've the vector space is indexed by set partitions, and so if I have a set partition whose block sizes are A1 through AM, then its coefficient in this linear combination is this product of exponentials with some signs. And the proof is a slightly involved, but elementary. Okay, so for each positive integer k, we have this quotient theory where we have an additional relation, the one I just described, and these somehow are analogous to the 2 plus 1 dimensional theory, Terraia-Vero theories that you can construct from the temporal Lieb category at a root of unity. So are they interesting TQFTs, or are they boring? Well, the beta 1 case, of course, is boring. The Hilbert space for, say, a closed 3-manifold has a basis given by this finite set, the Z2 vector space. And this, because things are always finite, we actually get a full 3 plus 1 dimensional TQFT. If beta is 2 or larger, it doesn't, we're still going to have 3 manifolds where the Skane module or the Hilbert space is infinite dimensional, and that means that we can't extend it to all 4 manifolds. And particularly, we can't extend it to that 3-manifold cross S1 because the answer should be the dimension, but if the dimension is infinity, that causes a problem. And so particularly, if I have an incompressible surface in a 3-manifold, then I can take a bunch of parallel copies of it, and these relations I described above just can't simplify those parallel copies. So that's kind of disappointing. But when beta equals 2, there is something interesting does happen. And that is, it turns out that for this manifold, so I've got the solid torus, and I put an arbitrary boundary condition, and that turns out to be finite dimensional for any boundary condition in this beta equals 2 quotient. And because, so what's special about S1 cross D2? Well, that is the attaching region for a two-dimensional four handle. I mean, sorry, a four-dimensional two handle. And so that means that we know how to compute a path integral. We know how to glue four manifolds along S1 cross D2. And in other words, we can construct a well-defined numerical invariant for four manifolds built out of not just 0 and 1 handles. That's always easy, but we also can do two handles. And this class of four manifolds is actually pretty interesting. I mean, there's a lot of open questions about this. Now, is this going to be a powerful invariant of four manifolds? I seriously doubt it. But I so far have not succeeded in identifying exactly what it is. There's I wonder if he's in the audience. Yes, so a Leon Gertz, a grad student at Hamburg is working not exactly on this, but on another theory that has a lot of similarities to it. So he might know the answer now, but I don't. But we do get a path integral, and it's going to be a function on surfaces in the boundary of these four manifolds. And notice that lives in an infinite dimensional vector space. So we have a well-defined vector in this infinite dimensional vector space. Okay, so in the little bit of time that's left, I want to talk about a completely different aspect of this. And it has to do with sort of exotic symmetric monoidal categories or exotic tensor categories. But to get there, let's think about four dimensions, but again, codimension two, so surfaces and four manifolds. So now I'm just gonna sketch briefly what goes on. Previously, we had a three ball with some curves in the boundary. Now we have a four ball with a bunch of circles in the boundary. In other words, we have a link in the three sphere. And so we're going to define a vector space for this pair. Now don't get, link invariants are interesting, but don't get too excited because this depends only on the Z2 unoriented linking matrix of the link. So as a link invariant, it's super weak. And so for example, if I have two circles that are not linked, and then there's there's a total of two partitions, and both of those partitions are realizable by surfaces. But if I have this link, the Hopf link, non-zero linking number, there is no way to have them both bound disjoint surfaces in the four ball. So the dimension of this space is sensitive to the linking number. And so now we can try to enumerate these linking matrices. That's kind of the same thing as a graph, where if I have an edge for each component of my link, and then a vertex for each component of my link, and I draw an edge if the linking number is non-zero odd. And so here are they all up to 6 vertices, and this first column is the dimensions. And the dimension, there is a lot of repetition, but we're getting different numbers. If you plug some of these into the online encyclopedia of integer sequences, you don't find them, which suggests that this is some kind of new combinatorics, not old combinatorics. Anyway, so it's computable. And the way you compute it is you look at partitions of the vertices of our graph such that the number of edges connecting two blocks of the partition is even. So just count those up. Okay, good. The timing is working out right. So previously for most of the talk, I was talking about a 3 category, and now I'm talking about a 4 category. And I remember like when I was in grad school, we would go, oh my goodness, one categories are bad enough. Now these guys want us to think about in categories. There was a lot of resistance. But now, decades later, I realized, no, it's actually really cool stuff, and it's very structured algebraically. And this talk is, really only scratching the, doing the preliminary work, but one could give a completely different talk about the, tensoring all these idempotents from previous slides together. And so in particular, sitting inside some in category is a large number of tensor categories and symmetric monoidal categories and braided things. And so let me just give you one example. So we're in a 4 plus epsilon dimensional TQFT. And so that means to a 2 manifold, like the disk with empty boundary conditions, we assign a 2 category. It's going to be pivotal. Okay, what's a 0 morphism in this 2 category? Well, it's a disk with a codimension 2 submanifold, because we're at k equals 2. And so here's a choice of a 0 morphism in this 2 category. What are the endomorphisms of this thing? Well, whatever they are, they're going to be a pivotal tensor category. Well, one object in this particular pivotal tensor category is given by, you should think of this whole picture as being inside B3. And it's basically, this is sort of a hop link, but we've chopped off the edges. So just the interesting part of a hop link. That's an object. It turns out it's not a simple object. It's sort of the tensor unit direct sum, a different object. And so this green thing I've drawn there, that means I'm somehow orthogonalizing with respect to the tensor unit, and now we get a simple summand. And then we can ask, okay, what tensor category does this guy generate? What are the dimensions of this Hom space? Is it something exotic like Deline's rep S sub t? So the dimension, the box space, so to speak, if I have a bunch of copies of C is that object above corresponding to the hop link. If I have an odd number of copies, it's 0 dimensional, and if I have an even number of copies, you get the following sequence of numbers. Again, not to be found in the Encyclopedia of Online Energy Sequences. And how are these numbers computed? It's partitions of a J-gon, J is even, such that adjacent vertices are always in different parts of the partition. That's the result of me sticking this in there. And the number of edges connecting 2 distinct parts is even. And that's what I said above, because the linking, if you glue these guys together, you get a daisy chain, sort of a bunch of circles linked up in a circle. And so this is just a specialization of what we said before. So that's how you compute these numbers. They're the Hom spaces of some tensor category. For J equals 6, here's the 16 partitions that I promised. The green sort of tells you how the vertices are getting joined together. And question is that a new category, or is it expressible in something else? And it doesn't seem like it has anything to do with representations of Lie groups or Lie algebras. I suspect it's new, but again, I think this in Dror's talk, I think he did a good job of emphasizing all the unknowns, which are often more interesting than the knowns. And so there's quite, in this topic, there's a lot that I don't know, and anyone's welcome to dive in and try to solve it, because my progress is, most of this was done 10 years ago, and I have not done a lot. Anyway, it's a big subject, and there's room for lots of people to study it. I guess I think I'm out of time, so I won't mention the relation with the Tup polynomial, but there is one. Somehow sitting in the 3-dimensional version is somehow the Tut TQFT, the TQFT that you build out of Tup polynomials. But I will stop right now. Thanks.